In the last video, we have altogether explained 11 properties of determinant of certain special matrices, and this video is only about the exercises on different kind of determinants. And please don't use the cofactor expansion from the beginning when I give you a problem. If you are able to spot out some special properties on the given matrix, and please apply the corresponding properties I explained in the previous video, and you're able to get the determinant very quickly. So please look at the current matrix, which is of the size 4 by 4. Are you able to tell me the determinant of M? If you use the cofactor expansion, it may be a slow process. So you can use the quick way. I explained already in the last video. It is a property 3, I think. So by the property 3, we understand that because it is an upper triangular matrix, we understand that the determinant is simply the multiplication of all the entries on the diagonal. So the answer is going to be minus 24, right, for the determinant. And let's look at the next case. So please look at the current matrix, which is 4 by 4 again. It will take you a long time to get the answer. If you try to apply the cofactor expansion formula to get the determinant, please notice some special thing about this matrix. The special thing is that, you see, the column 1 is basically the same as column 4, right? So, and by the property 6, you have to go back to the previous video if you forget. We explained that if the matrix has 2 rows or 2 columns identical, the determinant must be 0. We have explained it already. And let's look at another case. So please look at the current 3 by 3 matrix. Can you notice some special thing about this matrix? The fact is that, please look at the row 2 and row 1. I think row 2 is basically 2 times row 1. You have to check it yourself. And basically by the property 9, and obviously it is in the previous video, we understand that if it happens like this, the determinant M must be 0. So please look at the current problem. I'm not giving you the matrix M. I only tell you that the size of M is going to be 5 by 5, so it's a pretty big matrix. And the determinant is actually 2. Can you tell me the determinant of the matrix 3 times M? And 3 times M means it is a scalar multiplication, right? And based on the previous property 8, we understand that the determinant of this matrix is going to be the determinant of the original matrix M times the factor k to the power n. And n actually represents the number of rows or the number of columns of the matrix M. So it means this factor is actually k to the power 5. And the k actually means the scalar you're looking at. So it means the multiplication factor is actually 3 to the power 5. And it means the determinant in this case is 3 to the power 5 times 2, right? Because the determinant of the original matrix M is actually 2 here. So it means the determinant of our matrix 3M is gonna be 486. So once again, in the new exercise, I'm not giving you the actual entries of the 3 by 3 matrix M. I'm only telling you that M actually has determinant 5. And for the new matrix N, can you tell me the determinant of N now? Please notice what you are doing. What you are changing from M to N is you are multiplying the first row by 7, right? And based on the previous property 7, so I think it's property 7 now, we understand that our new matrix has determinant which is the same as 7 times the determinant of M. Because we know the determinant of the matrix M already, so it means the answer is 7 times 5, which is 35 now for the determinant of the matrix N. And let's look at the part B. So please compare the two matrices T and M. Can you see what you can do with M such that you can bring it to the new matrix T, and then from there you can talk about the relation of the determinants of the two matrices. You see, from M, what you are doing is maybe I can swap the first row with the last row. Can you see what's happening after the swap? And I think I'm getting this one. You see row 3 is swapped with row 1. And of course, in that case, the row 2 is unchanged. I think this matrix is not the same as T, but they are getting closer. I think the next swap I can use is I can swap row 2 with row 3. In that case, I get T. You can compare. If I swap these two rows, you will get the matrix T now. And can you tell me the relation of the original matrix with T? I think you're able to do that because, for example, if I let the middle matrix be N, the fact is that the way we swap the rows, we have discussed it already. It is the property 4 we have done in the last video. The determinant of this new matrix after swapping the rows one time is going to be the minus of the determinant of the old matrix M. And similarly, because we are swapping rows again for the matrix T, what we do is determinant T is going to be minus determinant of the matrix in the last step, which is N, and we understand the determinant of N is actually minus determinant M. You see, basically because of the fact that you swap rows two times, basically you're taking minus and then minus again. So it becomes plus again for the determinant M, right? It means actually the determinant of T is exactly the same as determinant of M. After swapping rows two times, you see they are the same. And let's look at one more case. So please look at the current matrix. Trying to apply the original formula for cofactor expansion is going to be a huge process because it's a 4x4 case. Can you notice something you can do on the matrix M to simplify it a little bit? And based on your understanding of the properties of various determinants, you can actually get the answer quick. You see, if you do the row operation on row 2, what you can do on row 2 is you do something like row 2 plus row 1. I'm doing it because I noticed that these two rows are pretty similar because row 2 is basically minus row 1, right? So if you do this, what you are doing is you're looking at a matrix like this, and let's say all the remaining spots are the same, but now you see the second row is totally 0, right? And based on the previous property, which is the property 4, we understand the determinant of this matrix is actually 0. So please look at the current matrix M here. Now the cofactor expansion formula is going to be long because M actually takes the size 4x4, right? And you have to use some previous properties to make the matrix simpler. And from there, we can find the determinant quickly. For example, please imagine that you can actually do some row operations quite same as how you solve the linear system by the Gaussian elimination. For example, what you can do is I can use row 2 plus row 1 for the row 2 because after adding the first two rows to update the row 2, what I have is the following. You see, I claim it's a very good strategy. Why? Because you see, I'm able to arrive at some zeros, and getting more zeros are already very beneficial for us to find a determinant. It makes the determinant formula easier. And also the fact is that if you recall our previous property 11, the determinant is actually not changed by a row operation like this. So I think on the same matrix, what we can do is we can do the same for the row 3 and row 4. For example, to update the row 3, what I can do is I can use row 3 minus row 1, right? If you do this row operation, what we have now is the row 3 like this. It is actually good because we get many zeros now. And also, you see, determinant once again is unchanged for a row operation like this. And for the last row, row 4, what I can do is I can use row 4 minus 2 times row 1. I hope you can see what's happening. If you do that, you have is you get 0, 0, 0, and the last spot is 2, right? Now please look at the new matrix. We have done 3 row operations. All of these are not changing the determinant. That's the key here. And also the fact is that for this matrix, which is upper triangular, right? And based on our previous property 3, we understand that this matrix has the determinant, which is the same as the product of the diagonal entries, you see? So it's 1 times 5 times 3 times 2, which is 30. And so it basically means the original matrix must have determinant 30. So we can obtain it pretty quickly like this. Unfortunately, if you try to use the cofactor expansion formula, it's going to be a long process. So that's the end of this video.